Hello viewers and my dear students. Welcome to the new chapter, that is modal analysis. I'll give you a demo on modal analysis of a cantilever beam. These are all offline video help files prepared by me, Dr. B. Gurdat, former professor and head, Department of Mechanical Engineering, Bangalore Institute of Technology, KR Road, Bangalore 4, presently working as professor at the Department of Mechanical Engineering, Nitte Meenakshi Institute of Technology, Yelahanka, Bangalore 64. Now, before we start with the demo of this model analysis of cantilever beam, I'll tell you the basics. First, we'll theoretically determine the natural frequencies and mode shapes and all that. Then we'll try to verify the same using Ansys release 14. Okay, now you see here, this is a simple cantilever beam fixed at one end, free at the other. Okay, cantilever beam subjected to free bending vibration. Now you see here, now if you give a force here at the end and all that, it will vibrate. See here, figure shows a cantilever beam with rectangular cross section. Is a rectangular cross section subjected to bending vibration by giving a small initial displacement at the free end. Now you see here, from this position, going till this, coming back till this, and coming here, this is, we call it as one cycle. Okay, this is one cycle. If this is done in 1 second, you call it as one cycle per second. If you convert this in RPM into 60, will give you the RPM. Okay, that is one cycle per second or 60 RPM. Let us say this, if I give it more force so that it vibrates at, that is going from this position to this position to this position and coming back to this position, if it does 2 times in 1 second, we call it as 2 cycles per second. If it does 5 times in 1 second, we call it as 5 cycles per second. If it does 10 times in 1 second, it is called 10 cycles per second. If it is 10, let us say 10 times per second, if it does, we call it as, this is vibrating at 10 cycles per second. Or if you multiply by 60, 10 into 60, 600 RPM is the frequency. Okay, cycles per second is, we normally call it as hertz. Okay, did you follow? I'm going to repeat this, please understand. From this position, going to, if you give a force at this, okay, initial displacement here, okay, by giving a force here, going from, coming to this, going to this, and coming back to this position, this is one cycle. If it does one cycle in 1 second, it is called 1 hertz. If it does 2 cycles in 1 second, it is 2 hertz. If it does 3 cycles in 1 second, 3 hertz. If it does 5 cycles in 1 second, it is 5 hertz. In that way, this is the thing. If it does, let us say 10 hertz, that is 10 cycles per second, we call it as 10 hertz. And if you multiply by 60, it will be 10 into 60, 600 will be the RPM. Okay, this basic concept of hertz or cycles per second or RPM, you please understand. Okay, now this I have given you the basics. Let us say in case it does this one cycle in 2 seconds. Okay, then we call it as 0.5 hertz. Okay, this cycle, okay, that is going to this, coming back to this, and coming back to this, as a coming back to this initial position. If it does in 4 seconds, we call it as 1 by 4, 0.25 hertz. Okay, now understand this basics. Hertz, you should clearly know what exactly is hertz. Hertz is cycles per second, and multiplying by 60, it is called in RPM. Okay, now as I said, that is, if it does 10 cycles per second in 1 second, if it does 10 cycles, okay, then it is called 10 hertz. 10 hertz is same as 10 into 60, okay, that will be 600 RPM. Okay, this is the basics of hertz and all that you remember. Okay, okay, now you see here, I'll give you some of the introduction here. These are all very important from this subject point of view. Very important, carefully understand. See here, first I'll give the definition of natural frequency. Natural frequency is the rate at which an object vibrates when it is disturbed. As I just now said, it is the rate at which an object vibrates when it is disturbed. That means the unit will be in cycles per second. That means it can be 10 cycles per second or 20 cycles per second or 80 cycles per second. Okay, or frequency in hertz. If it is 80 cycles per second, it is vibrating means it is 80 hertz, you say. If it is vibrating at 100 cycles per second, you say it as 100 hertz. Okay, now in the same way, see here, first we'll do the modal analysis. No, I told you modal analysis is the first thing to be analyzed. Very important from the subject point of view. As a designer, you should know the basic concept of this modal analysis and all that. See here, modal analysis. This is used to determine the natural frequencies and mode shapes, or that is vibration. This is usually called as vibration characteristics of a structure or a machine component while it is being designed. Okay, this is mainly used to determine the natural frequencies and mode shapes. These things anyway we are going to prove that whatever we got it by theory using Ansys also. Okay, we'll determine the natural frequencies and mode shapes. To explain in a simple way, modal analysis calculate the natural frequencies of your system so that you will know which are all the frequencies can be destructive and dangerous, and we must avoid these frequencies. See here, this you try to understand. See here, let us say for a rotating shaft, let us say, I'll get the natural frequency as, that is 30 hertz, let us say. 30 hertz means 30 cycles per second. Okay, if it is 30 cycles per second, it is 30 into 60 will be the RPM. Okay, that means 1800 will be the RPM. That means the natural frequency of this will be 1000, that is for a rotating shaft. If it is rotating at some 30 cycles per second, that is if the that is cycles per second for the rotating shaft, let us say if it is 30 hertz, that is 30 cycles per second if it is rotating, 30 cycles per second, if it is into 60 means it will be in RPM. 30 into 60, 1800 RPM will be the natural frequency. That means you should clearly understand, when you get 1800 RPM, this is the natural frequency of this. First, you will have so many natural frequencies. I'm talking about one natural, first natural frequency. I'm just giving you an example. Okay, 1800 RPM is the first natural frequency. That means, here as I said, which are all the frequencies can be destructive and dangerous. That means 1800 RPM will be dangerous, because if you know very well for this shaft, if you know very well for this shaft, it is 1800 RPM is the natural frequency. If it rotates also 1800 RPM, resonance picks up and there will be massive amplitudes developed, and as a result there will be massive stresses and the structure might collapse. Okay, that is why the importance of modal analysis is, what are all the natural frequencies you get for a system. Okay, those frequencies you should not operate, because if you operate at that frequency, the resonance picks up. Now I have told you what exactly is resonance here. This describes the phenomena of increased amplitude of vibration. See here, at resonance, when the natural frequency coincides with the forced frequency, you get the resonance. This describes the phenomena of increased amplitude of vibration that occurs when the frequency of periodically applied force, okay, that is forced frequency, is equal or close to the natural frequency of the system on which it acts. This will be demonstrated later in harmonic analysis. Okay, you should understand, if the forced frequency matches with the natural frequency of the system, then the resonance picks up, and you should avoid this point. That is, if you get first natural frequency as some 800 RPM, you should avoid 800 RPM. If you get second natural frequency as 1500 RPM, you should avoid 1500 RPM. If it is 2000 RPM, is 2400 RPM is the third natural frequency, you should avoid 2400 RPM. You can operate at any other region. There the amplitude of vibration will be lesser. But if you operate at the natural frequency, if the shaft is operated at its natural frequency, there will be massive increase in the amplitude of vibration and massive noise will be there, and this resonating, when the resonance picks up, there will be massive stresses developed. As a result, the structure is likely to collapse also. Okay, that is the concept of resonance and all that, which I'll be going to explain in detail later on also. Okay. Okay. Here, now I am going to touch upon this. Here, modal analysis. For the beam shown, this is the beam, okay, a cantilever beam, okay, for the cantilever beam shown. it is 1 meter in length, 0.01 meter, that cross section is 0.01 meter, that is width, and 0.01 meter depth also. Modulus of velocity is this, 2.068 into 10 to the power of 2.068, here 5 plus 10 to the power of 6, 11. 2.068, 10 to the power of 11 Newton per meter square. Density is 7,830 kilogram per meter cube. This is the thing. For this cantilever beam, I am going to find out the natural frequencies. First natural frequency, second, third, fourth, fifth, any number of natural frequencies can be determined. You will know well in advance what are the dangerous frequencies for this, which you should avoid. Okay. Now in that way, I will find out the natural frequencies. Initially, I will tell you how to do it by theoretical methods. Okay. See here, please see. Now you see here. See here, this is a cantilever beam. Okay, of length L. Okay, length L may be 1 meter here. Okay. Now, the natural frequency is given by this. First natural frequency is given by W1, 1.875 square root of EI by ML to the power of 4. Okay, W2 will be this, W3 will be this. These are all the first 3 undamped natural frequencies and mode shapes of the cantilever beam. This is the mode shape. That is how at the critical, that is at this natural frequency, it bends this way. At this natural frequency, it bends, the shaft bends this way. At this natural frequency, that is the third natural frequency, the shaft bends this way. These things anyway we are going to prove in Ansys sessions. Okay. Now as you see here, this you remember, this is the formula. This will be in radian per second. We'll convert into here we'll convert into circular frequency. If lambda is the eigenvalue, W is root of lambda square. That is circular frequency is 2 pi f. Okay. That is W is the circular frequency, that is 2 pi f. F is the frequency in hertz. This is cycles per second. Okay, F is the frequency. That is F is in place of omega. F is equal to omega by 2 pi. That means wherever you have omega, no, that is here I will substitute 1 by 2 pi. You see here, this is what I am doing here. This is F is frequency in hertz. Okay, cycles per second. N is 60 F. That is if you convert into RPM. Now F1 is 1.875 square divided by 2 pi I2. So that once you divide by 2 pi, this is circular frequency. This is frequency, F frequency in hertz. I want frequency in hertz. That is why I'll divide by 2 pi. First one is 1.875 square divided by 2 pi. EI by ML to the power of 4. E is the Young's modulus. I is the moment of inertia of cross section. M is mass per unit length. Okay. Mass per unit length is, that is rho into area of cross section. Okay. Rho into B into D. L is the length of the specimen. Okay. Now you see here. E is the Young's modulus of the material. I is the moment of inertia. Mass per unit length. Okay. Mass per unit length. That is rho into B into D. Or B into rho is the density of the material. B into D represents the cross-sectional area of the beam, D being the depth. Now you substitute that 1.875 square by 2 pi, E into I is BD cube by 12, okay, by rho L to the power of 4, you see here, rho M L to the power of 4, M is rho into BD, you cancel off BD here, it becomes E into D square over 12 rho L to the power of 4, okay. 12 L to the power of 4. That means now you substitute for this. E2 into the 10 to the power of 11. This is 0.01 square. Okay. 12. 7. This is density. Length is 1 meter. That is 1 to the power of 4. In that way, you get first natural frequency as 8.16 hertz. In the same way, you substitute. This will be same 212.8. Second one is 4.694 square by 2 pi into root of 212.8. Second natural frequency is 51.15 hertz or 3069.3 RPM. Third natural frequency is in the same way if you do 143.25 hertz or 8595.07 RPM. These are all the theoretical things what we are going to prove in Ansys. Okay, this is the session 1 on modal analysis. Thank you very much for viewing. We'll continue this in session 2. Thank you very much.